Welcome to the central force problem. Today we are going to discuss the motion in time in the Kepler problem. From the law of conservation of energy, if we integrate it for time, we can obtain the expression here, which gives the time as an integral over the radial coordinate, starting from the initial value up to some radius r. And of course, in order to carry out this integration, in principle, we need to replace the radius by the orbit equation and carry through. An alternative approach would be to start directly from the conservation of angular momentum, solve it for the differential of time, and then use the orbit equation 355 in order to arrive at the integral here, which solves for time by integrating from the initial value of the polar angle up to some angle theta. Uh, Both of these integrals can be carried out in terms of elementary functions, but the relations are very complicated, and obtaining r and theta as a function of time poses formidable problems, essentially because it would be very difficult to invert these expressions in order to obtain the inverse relations. Now, a particular case that is fairly easy to treat is that of the parabolic motion, which corresponds to an eccentricity being equal to 1 and a particular choice of the integration constant for the polar angle being chosen as 0, such that the plane polar angle is measured from the perihelion and time is measured from the passage through perihelion. Then in this case, if we use the trigonometric identity here together with equation 366, time is given by the integral here, and this can be solved in a straightforward way through this substitution. So tangent of theta over 2 is some variable x, and then time can be calculated as this integral, which is straightforward to carry out and leads to the result here. Now, if we take theta belonging in the range from minus pi to pi, then this shouldn't be here. Then when when t tends to minus infinity, the particle approaches from theta uh, asymptotically given by minus pi. At t equals 0, the particle passes through perihelion, and at t tends to infinity, theta will tend to pi, so the particle moves infinitely far away. And solving this cubic equation in tangent of theta over 2 and inverting the solution will determine theta as a function of time, and then the radius as a function of time will follow through the orbit equation. In the case of elliptic motion, one introduces the eccentric anomaly psi through the relation here. So we denote the radius as being the semi-major axis multiplying 1 minus e cosine of psi, where e is the eccentricity. Now for psi belonging in the range 0 to pi, uh, we have the two limiting situations where for psi being equal to 0, the distance given here is simply the perihelion, and from psi being equal with pi, we obtain the aphelion radius. Then if we go back to equation 365 here, and we specified for the case of elliptical motion for the radius and the energy formula, we can write the integral in this way, with r0 being the perihelion radius. And then if we use the transformation that we suggested here, with r given as a function of the eccentric anomaly, then we can recast the integral in the form here, which is obviously a straightforward, very straightforward calculation. In particular, if psi is equal with 2 pi, then we obtain the period of the motion through the formula here. Another way to obtain this result is to start directly from Kepler's second law, from the constant areal velocity. So if we take Kepler's second law and we simply integrate it over a period of the motion, we obtain the total area swept by the radius vector being equal with the quantity here, angular momentum, multiplying the period and divided by twice the mass of the moving body. Now, since the orbit is elliptical, the area of the ellipse is simply pi multiplying the product between the semi-major and semi-minor axis. The semi-minor axis is given in terms of the semi-major one by the formula here, and then together with the result 362, we once again obtain the expression for the period of elliptic orbital motion. And this very important result states that the square of the period is proportional to the cube of the major semi-axis and is known as Kepler's third law in the approximate form. To obtain the exact form, we need to remember that the mass of the particle being discussed here is in fact the reduced mass of a two-body system, and that the force constant itself is given by the product between the masses of the two bodies and Newton's gravitational constant. Then, using the result 371 together with 373, we obtain the exact form of the period given here, which is approximately equal with something similar to our previous result, in the assumption that the mass of the particle can be neglected with respect to the mass of the Sun. So the square of the periods of the various planets are proportional to the cube of their major semi-axes with varying proportionality constants. These are all the same if the masses of the planets can be neglected with respect to the mass of the Sun, but this isn't always the case, as is, for example, the situation with Jupiter. As an application, consider the case of two celestial bodies which are moving about their common center of mass in circular orbits having the period tau. Suppose that somehow they are stopped and then released, being allowed to fall upon one another. How long does it take for them to collide? If we used Kepler's third law for the specific case of circular motion, then we can write the radius of the circle as function of the period through this expression here. Then after release, the two bodies will no longer possess any kind of angular motion, so they will fall upon one another by virtue of Newton's second law. And we know how to integrate such expressions, as we have used very similar methods in the past. So we multiply both sides by 2 times the radial velocity, and then we can immediately perform the integration here, which implies that the square of the radial velocity is this quantity plus a constant, and this constant can be determined from the condition that the radial velocity is originally zero. So at the initial moment after the two bodies are stopped, and then they are allowed to fall upon one another. So from this condition we can obtain the integration constant as the value here, and then we can simply write the radial velocity as this expression. And then if we carry out the integration for time, we need to solve the integral here. And this is done by the substitution r divided by r0 being equal with u. This leads to the time t0 being given by this. So t0 would be the time until the two bodies fall upon one another, being given by this integral, which is carried out immediately for the substitution for the variable u being equal with the squared sine of x. If we use this transformation, then we can recast the integral in this form, and this is equal simply with pi over 4. So the conclusion is that t0, the the time it takes for the two bodies to collide by falling upon one another, is the period of the circular motion divided by 4 times the square root of 2. As another example of an application of Kepler's third law, consider the periods of the Sun, Earth, and Earth-Moon systems. If we can write Kepler's second law for both instances, and if we then take the ratio of these two expressions, we find first the ratio of the two periods as as given by the quantity here involving the ratio of the radii of the Moon and the Earth and the ratio of the masses of the Sun and the Earth. And if we solve this for the ratio of the masses, we obtain the ratio of the mass of the Sun to that of the Earth as being equal with this expression. So the square of the ratio between the Earth-Moon and the Sun-Earth periods, and the radius of the Earth divided by the radius of the Moon cubed. Now, these quantities are all known, so we know the periods of the two orbital motions in days. We know the radii in meters, and as such we can calculate the ratio of the masses from the for the Sun and Earth to be given by the value here, and the standard value is this one. So you can see we can obtain the a very good agreement with the standard value by a simple application of the Kepler's third law and these known constants. Now the frequency of the motion is defined here, the frequency of periodic motion, and the period itself is given by Kepler's third law. So from these two, what follows immediately is that the frequency in the case of elliptical motion is given by the square root of this ratio involving the cube of the semi-major axis. Now, as we have seen in the case of elliptical motion, time can be integrated straight away for the eccentric anomaly to give the result here. And if we use this together with the expression 375, we obtain what is known as Kepler's equation, written for what is known as the mean anomaly, omega t, so the frequency multiplying the time, which is again a quantity defined over the range 0 and 2 pi, so it's a periodic quantity. Now, once the mean anomaly is known, then one simply inverts equation 376 in order to obtain the eccentric anomaly, which then provides the radius for the transformation 3.78. And now, so this is the transformation. This is the orbit equation, which is generally true for the Kepler problem. So from these two, one can solve for the polar angle to find the expression here in terms of the eccentric anomaly. And if we continue if we continue working with it, we can solve for the polar angle to obtain the ratio here. For this expression, we can separately add and subtract 1, and then if we take the ratio of the two expressions, we end up with the result here, which can furthermore be worked out a bit in order to simply provide the tangent of theta over 2 as being proportional with the tangent of psi over 2, where the proportionality constant is the square root involving the eccentricity of the motion. So the polar angle follows from the eccentric anomaly either through the result 377 or 378. And the requirement to solve Kepler's equation accurately over a wide range of eccentricities contributed to much of the development of numerical methods in the 18th and 19th centuries. And of course, the most accessible measurements and problems were related to astronomical observations. Now, we can derive Kepler's equation directly from the conservation of energy. So starting from the expression of the energy for the Kepler problem, we can solve this for the radial velocity to obtain the result here, and then we can just use the formula equating the total energy and the semi-major axis to work out the following expression, where we can then also use Kepler's third law with the following identification for the frequency of the motion. And putting these things together, we obtain the boxed result here. Now, remembering that in the case of elliptical motion, we wish to define the the radius in terms of the eccentric anomaly through this expression. If we take its time derivative, we obtain the result here. And if we use this together with the equation 1, then we immediately obtain this differential form, which can be integrated straight away to give us the known expression of Kepler's equation. In the case of eccentricities that are much smaller than 1, Kepler's equation can be solved numerically through the following iteration method. So in order n, the eccentric anomaly is going to be given by the mean anomaly plus e times the sine of the eccentric anomaly in the previous order. Then, so to first order, we would obtain the eccentric anomalies equal to the mean anomaly. In the second order, we uh, obtain the mean anomaly plus e, multiplying the sine of the mean anomaly. And into third order, we would have to take this expression, the mean anomaly plus e times this sinus of the previous result. And in order to work things out, we need to take we need to use trigonometric identities to expand the sinus, but furthermore, we need then to use second order expansions of the trigonometric functions themselves in order to obtain the result here. So you see it goes up to the uh, up to the fourth order in the eccentricity for the third order in the eccentric anomaly. In order to obtain a general solution of Kepler's equation, we can consider the following Fourier expansion of the eccentricity multiplying the eccentric anomaly. So it's a Fourier series in the sine of the mean anomaly with unknown coefficients, and our goal is to obtain these coefficients. In order to find them, the first thing we can do is take the integral here from 0 to pi out of this quantity multiplying a sine of m omega t, so where the m multiplying the mean anomaly with the mean anomaly as the integration measure. And then if we replace uh, uh, e times the sine of the eccentric anomaly by the Fourier expansion, we end up with the integral here, which this one is just Kronecker delta. It contracts with the sum, and the conclusion is that for a given coefficient in the sum, a index n, its value follows from this particular integral. And in order to go further, we can, and now the goal is to try to integrate by parts. So if we take the derivative with respect to the mean anomaly from this expression, we obtain the difference here, and we can isolate our integrand and solve for it to obtain this expression. And if we bring this back into the result 1, it follows that pi times a index n is given by the integral here plus the second integral evaluated between the endpoints. And now it is clear that from Kepler's equation and from the definition of radius as a function of the eccentric anomaly, it's clear that the eccentric anomaly at the origin is 0, and that pi, it is equal with pi due to being a periodic function. As such, the second term here vanishes, and pi over n is given by the pi times a of index n is given by the integral here. Now, if we once again go back to the Kepler equation and we take its differential, we obtain the form here, and then if we put these two together, we can rewrite the product between pi and the coefficient an as the integral here minus this term, which is evidently zero by straightforward evaluation. As such, pi multiplying the coefficient a of index n is given by this simple integral, which can be evaluated further through, once again, through the means of Kepler's equation. So if we bring this in here, we can rewrite the coefficient as this result, 1 over n times 1 over pi multiplying this integral. Now the reason we have done this is because the result here happens to be the integral representation of a Bessel function of order n and argument n times the eccentricity. So in effect, we have found the coefficients of our Fourier series, and we can write E multiplying the sine of the eccentric anomaly as the sum here, and in conclusion, taking this back to Kepler's equation, we finally obtain the solution here. So the eccentric anomaly is the mean anomaly plus this expansion, this Fourier expansion of in Bessel functions. Now, in the case where the argument of the Bessel functions obey this condition, so loosely speaking, for small arguments, then the Bessel function can be approximated as a power function. So it's given by the result here, and then using the definition of the gamma function, we obtain this expression, and as such the solution can be simplified further to this result, and it can be checked that it will provide for small eccentricities, it will provide the exact same results as the previous iterative approximation that we have presented. As an example of its use, knowing the eccentricity of Earth's orbit to be given by the value here, and the anomalistic year, or the period between successive perihelion transits, to have this value, we can calculate, for example, the angular motion of the Earth in 1/4 of the anomalistic year. And it turns out, through the use of Kepler's equation, that this is equal with an angle of 91 degrees, 55 minutes, and 18 seconds. Now, an interesting problem which sometimes shows up even in science fiction literature is that of the so-called Planet X, or Planet 10 maybe. So an Earth-like twin planet having identical orbital parameters. And what we are to do is to investigate to first order in the eccentricity whether or not this twin would be visible from Earth in two situations. The first one is the situation where it lies in the same orbit with Earth, but out of phase by 180 degrees, so as measured from starting from Earth's transit through perihelion, and another situation where it lies in an orbit rotated by 180 degrees with respect to Earth's orbit at the same perihelion transit time. And to carry out this investigation, we we begin from Kepler's equation and from the radius written as a function of the eccentric anomaly in the case of elliptical motion. And from these two things to first order in the eccentricity, we have this expression for the radius, and then we can write the initial radius of the Earth is just the perihelion point, while the radius of planet X is the aphelion, both being measured from with respect to the Sun, which is located at the origin. Now, from the conservation of angular momentum up to some integration constant theta prime, the polar angle is going to be given by this integral, and then we can calculate, for example, the polar angle for the Earth as a function of time is just given by the expression here. So we just replace our squared with this expression, and then working to first order in E, we obtain the result here, which can again by carrying out the Taylor expansion to first order in E, it can be reduced to this form. So here we simply neglect when we open up this binomial, we neglect the term the square term in the eccentricity, and then when we perform a Taylor expansion here, assuming that this is a small quantity, we obtain the result here. And this is of course a very straightforward integration, which gives the polar angle of the Earth as a function of time through this expression. Similarly, we can work things out for the polar angle of planet X in order to obtain the result here. And now if we define the angle alpha as the difference between the two polar angles, we obtain this expression, and we can see that its cosine is equal with -1, approximately equal to -1, and its sine is approximately equal with the quantity here. So it's proportional to the sine of the mean anomaly. To understand things further, we require a small diagram. So if we are assuming that the sun is here, and let's say the Earth is here. Initially, we started out at perihelion, so let's say the Earth was okay. Perihelion would be further away, but we've moved the Earth here. The correspondingly, planet X would be planet X started at aphelion. Let's say it ended up somewhere around here, and then so this would be RE. I'll write it like this, so it's a bit easier, and this would be Rx. And in this case, the angle alpha would be the one here. And what I will denote as the radius Rex is this. So it's the distance from the Earth to planet X. And what you will see as the angle theta S and X is going to be this angle. So this is going to be theta S and X. So as seen from the Earth, I am interested in the angle measured between the position of the Sun and the position of planet X. This is essentially what I'm trying to calculate. So in any case, it is clear that it should be clear from this diagram that applying the law of cosines for Rex, we need to evaluate the square root, which, given the value of alpha and the values of the two radii is approximately equal with 2 times the semi-major axis of the orbit. And then by the law of sines, in this diagram we can obtain the sine of theta S and X, so the angle measured between the position of the Sun and planet X as being approximately equal with the quantity here. Then um, at when the mean anomaly is equal with pi over 2, so a quarter way through the orbital motion, this sine is going to have its maximum value, because then the sine of the mean anomaly is 1, so this sinus is the expression here. And if we use this together with Kepler's third law, we obtain the maximum value of this sinus as being given by the quantity here. Now, for Earth's orbital constants, if we replace these with the known values of the orbital angular momentum, of the eccentricity, Earth's mass, the mass of the Sun, the semi-major axis, and so on, it follows that this angle is of approximately 1 degree and 50 minutes. At the same time, the apparent angle measured between the center of the Sun and the outer radius of the Sun, as viewed from Earth, it can be approximated for this calculation. So the tangent of this angle is simply the radius of the Sun divided by the semi-major axis of the Earth's orbit. And if we do the calculation, it turns out that this angle is simply equal just to 15 minutes and 48 seconds, to an angle of 15 minutes and 48 seconds. And therefore, in this particular case, in principle, through one astronomical method or another, the planet would be visible, as this angle is much greater than this one. However, if we were to work with in the second case by exactly the same method, it turns out that in this case the two planets are moving in phase, so their radii are equal through the expression here, and then we can evaluate the angle theta, the polar angle, as being given by this quantity, and alpha is, in that case, the angle alpha is simply equal with pi, and as such the apparent angle between the Sun and planet X as viewed from Earth is always 0. So in this particular case, the planet X is always hidden behind the Sun and is not visible from Earth. For the case of hyperbolic motion, we can begin by looking at the situation at perihelion. So in this case, the ADA energy is positive. At perihelion, it will have this expression, and we can find the perihelion radius immediately as being given by this quantity, with the constant A being equal with K divided by 2 times the energy. So it's a very similar expression to the elliptical case, but now this constant no longer has the significance of a semi-major axis. In any case, we can define the radius through the expression here, where the role of the eccentric anomaly is played by the quantity f. So given this expression, we can just take its time derivative to obtain the formula here, and then bringing this into the expression of the energy, we can integrate for time to obtain the result here. And in here we once again use the expression of r as a function of f to to get to the integral here. Now, so this integral is evaluated from perihelion to a given radius r, and to these endpoints there will correspond to different values of this variable f, which are just f0 and the one here. But we can evaluate f0 knowing the value of the perihelion radius, and then calculating through this expression to what value of f0 this would correspond. And it turns out that f0 is in fact equal to 0, and as such that the time in hyperbolic motion is given through the equation here, which is, as you can see, it is somewhat analogous to Kepler's equation for elliptical motion. We can now begin discussing perturbed gravitational motion in a very simple way, using the results developed so far for the Kepler problem. As a first example, we can consider a perturbation caused by a uniform distribution of dust in the solar system, which adds to the gravitational attraction of the Sun the linearly restoring force given here, where c is a constant proportional to the gravitational constant and the density of the dust, and the radius r, the radius vector r, is the sun planet radius. We are to assume that this additional harmonic force is very small compared to the direct gravitational force. So a representation of the combined potential resulting from the Kepler potential and this harmonic term would be this one, where I've tried to choose realistic parameters for the orbital motion of the Earth, and so the radius here is given in astronomical units. The effective potential is just measured in joules, and the idea is that with realistic parameters, there on this plot, this contribution isn't really visible. You end up with more or less the normal effective potential, having the Kepler term and the centrifugal term. So, in any way, to begin this investigation, we will first look at the case of circular motion. So, on the one hand, in the case of circular motion, from the conservation of angular momentum, we have the angular velocity simply given by the angular momentum divided by the mass and the radius of the circle squared. And in this case, we know that the applied force at this given radius is furnished by the expression here. So it is just the gravitational force and the linearly restoring force due to the presence of the dust. And we also know that the circularity condition demands that the applied force is equal with the minus the effective centrifugal force. So from these things, from these results, we can eliminate the angular momentum out of this formula, and we can write the angular velocity in terms of constants as given here. And then, since the period of circular motion is just 2 pi divided by the angular velocity, we obtain the result here. So this would be the period in in the combined field of having both the gravitational effects due to the sun and those due to the distribution of dust. And we can compare this with the period of circular motion in what would be a pure Kepler problem. So putting the two together, we finally find this relation between the period in the perturbed gravitational problem and in the in the unperturbed case, which is the result here. Given, of course, to first order in C, so we expand here while keeping into account that this is the contribution of the harmonic term is very small compared to the Kepler term. Now let us consider the case of small oscillations about circular motion, and we will use the method that has been exemplified in the previous calculations for the motion on a paraboloid or motion in the Yukawa field. We consider that the radius is a function of time, given by the circular radius plus a small oscillation s, such that the derivative of r is with respect to time is just the derivative of s, and we will be using the circularity condition here and the general expression for the energy in this field, which includes the kinetic term, the centrifugal term, the Kepler term, and the harmonic term. So if we, like we did previously, if we expand the energy up to second order in the ratio of s to r0, and then we renormalize such that the constant term is removed, we obtain this new energy E prime, which corresponds to simple harmonic motion. So for a harmonic oscillator of mass m and spring constant kappa, which involves both the contribution from the Kepler potential and one from the harmonic potential. And for this harmonic oscillator, we can calculate the period straight away to obtain the period of small radial oscillations about circular motion as given here. And notice that since this quantity here, the denominator here is smaller, so overall this entire term is greater, and as such t prime will be smaller than t, because since this one is larger, this one is smaller, so overall the parenthesis here is larger, so t is greater than t prime. Now it turns out that the motion in this perturbed field is given by a precessing ellipse, and to see this we begin by writing the total potential, which is the Kepler term plus the harmonic term. But now we need to recognize that the constant here c follows from the gravitational constant and the distribution of dust in a sphere having a radius given by the radius of the planet with respect to the sun at a given moment. So if we choose C to be of this form, then we can recast the potential as a sum of two terms which are both varying as essentially as 1 over r. So the first one is the pure Kepler term, and the second one is, to this we add a term involving the Newton's constant times the mass of the planet divided by the radius and times the total mass of dust at that given radius, which is essentially it is the term here with volume integrated for this choice of the constant. And the idea is that if we write the potential in this way, then we can factorize the Kepler term and write it as the Kepler potential multiplying 1 minus this ratio, the mass of dust, which affects the planet at a radius r, divided by the mass of the sun. So obviously, as long as this quantity is small with respect to 1, essentially we are we are describing the motion in a perturbed Kepler field. And then if we wish to calculate the precession of the ellipse on which the motion takes place, we once again define this angle phi as a product between the angular velocity for circular motion and the period t prime of small oscillations around it, which is just the product here. And to first order in the constant c, the expression that remains is this one. And then we can find the angle omega as phi minus 2 pi, and its rate of change is simply its value divided by t prime. So the result is the one given here. So the rate of precession is of the ellipse is the quantity here, and with it being negative, it would imply that the precession is undergoing a clockwise rotation. Another type of perturbation that we can discuss involves the motion of a particle in the field given by the Kepler term, to which we add a constant h divided by r squared. So this would be a potential varying as the inverse square of the distance. And again, we are assuming that h is very small compared to the angular momentum contribution to the effective potential. So this is going to be a small correction to the unperturbed motion, which is given by the standard Kepler problem. And if we try to plot this once again for parameters that make sense in case of the Earth's orbital motion, and in hindsight with parameters that make sense for a perturbation that would account for the deviations from a Keplerian orbit, then really on a plot you cannot really see this contribution. It once again just looks like a standard effective potential for what would be Earth's motion in the gravitational field of the sun. But the analysis follows the same steps that we have already seen in the previous examples. So if we were to look at small radial oscillations about some circular radius rho, then we would write the radius as a function of time in this way, and this would be the radial velocity. The circularity condition at the value rho of the radius would be given here, and the total energy would also follow through this expression, which includes the kinetic term, the centrifugal term, the Kepler term, and our perturbation. Putting all of these things together, expanding the energy up to the second order in S over rho, and using the circularity condition, renormalizing things so as to remove the constants, we end up with this expression. Once again, there's a simple harmonic oscillator. And then from the value of the equilibrium radius rho, which is given here, and the definition of the period, we can calculate the period of small oscillations as being the quantity here. Then if we want to look at a possible precession rate in such a field, we calculate the angle phi as the product between the angular velocity for circular motion and the period of the perturbed motion, to find the expression here up to this should be written up to first order in h, because it's assumed that this is a small quantity, and then the precession angle would just be this the difference between this angle phi and 2 pi, and the precession rate would be just the ratio between this angle and the period. and the result is the one given here, which once again suggests that for this particular choice of the perturbation, the precession angle is sweeping clockwise through the plane of the motion. What's important to note is that if we were to assimilate the perturbation here to a change in the effective potential, so effectively to a shift in the value of the angular momentum, so we could write the effective potential like this and just redefine the angular momentum according to this new value. And in that case, if we were to study perturbations around circular motion, the equilibrium radius would simply have the expression here, and then the period would simply be given by Kepler's third law for motion in elliptical orbits, and as such the angle phi is exactly equal with 2 pi, and the precession angle is 0. So there is no observable precession of the ellipse, and this is due to the fact that changing the angular momentum simply defines a new solution of the Kepler problem according to the new value of the eccentricity, rather than perturbing an existing solution. So it's just a new exact solution of the Kepler problem, having an orbit equation which results in an ellipse, and no precession is involved. In summary, we have solved the problem of finding the motion in time in the Kepler potential for all possible orbits, and have derived Kepler's third law of planetary motion in its approximate and exact forms. For elliptic orbits, we have studied Kepler's equation in detail, providing iterative and analytical solutions along with various applications. We have analyzed the motion in perturbed bound Kepler orbits for harmonic and inverse square law perturbations. In the following, we will discuss the Laplace-Runge lens vector. That being said, I want to thank you very much for watching the video. I hope it was worth your time, and I will catch you later. Goodbye.